In this video lecture, we will learn the remainders theorem, and first let's recall the context. And the context is the following. We have previously learned that for any given function, we can use the formula and create a series like this, which we call the Taylor series, and ideally this series is equal to this function for some values of x. However, we didn't convince ourselves 100% that this sum values of x is exactly the same as the interval of convergence. And later we have done the following. We said, okay, well, we may not be interested in all infinitely many terms of this particular series, and let's say what happens if we are only interested in the first or up to kth term, let's say, and then what happens in this case is that we take the series and we separate it into two parts. So the first one has k plus 1 terms, and the other part has the remaining tail of the series starting with a key k plus 1th term and all the way to infinity. And the first part is then now becomes a polynomial, which we refer to as the Taylor's polynomial of degree k. And what's left is what we refer to as the remainder, and we can also use the index k here to identify this remainder, but the remainder is actually has infinitely many terms. And the idea is that the function being equal to the Taylor polynomial plus the remainder actually like this whole business of Taylor series being equal to the function on its interval of convergence is only possible when the remainder, like when this part, actually goes to 0. So this is kind of the idea behind proving that the Taylor series that we have created actually converges to the function from which it was originated from. And while we are not going to prove this, it is true that for all these functions that we have studied and for which we have found the Taylor series, such as sine, cosine, arctangent, ln of 1 minus x, e to the x, and so on and so on, all those functions actually have their interval of convergence being the same as the interval on which they match the f of x. So basically, in other words, these functions on the interval of convergence converge to the function from which they were originated. And this proof, which we are not going to do in this class, but this proof is based, or it heavily relies on the following theorem, which we call the remainder theorem. And here's the statement of the theorem. The theorem basically says that the remainder of the Taylor series is bounded by the following expression, where m is the upper bound the n+1th derivative of the function on some interval. And this theorem, besides having this application of us now being able to prove that the Taylor series for a lot of these nice functions actually converges to the function, has many other applications, which we are going to discuss next. And to start with the applications, so again, we're gonna have to remember this inequality, and to start, we're going to consider the following example. So let's consider computing the following expression. So what is cosine of 0.1? And to do this, I guess let me rephrase the task. So let's use M4, the Maclaurin series of cosine function, to estimate cosine of 0.1, and we're going to do it in steps. So the first step is, let's find M4, the Maclaurin polynomial, and we're going to use the fact that cosine of x is equal to, and let me recall that myself first. So cosine of x, Maclaurin polynomial, is this. So we have, it's an alternating series. So this is the Maclaurin series, and we're going to take the first four terms, not the first four terms, but up to x to the power 4th of this series to construct the M4. So M4 is, so when n is 0 we have x, when m is 1 we have, actually I definitely made the mistake copying this over. Cosine is an even function, so it makes sense that it only has even powers here, right? So so the first term is actually when n is 0 we have 1, when n is 1 we have 1/2 x squared, when n is 2 we have 1, 2, 1, 4, so 4, 3, 2, 24, x to the power 4. So this is the 4th degree Maclaurin polynomial for this function. Now we're going to estimate cosine of 0.1. So basically what we're doing is something that we've done in the previous lesson. We're using Maclaurin polynomial to estimate the output of the function. So cosine of 0.1 can be estimated by this, and this can be easily computed without a calculator. And again, try not to use a calculator here. So 1 minus 100, so it's 0.02. And so divided by, it's not 0.02, it's 0.01 divided by 2, so it's 0.05. Plus, here we have 0.01 to the power 4, which is this, and we dividing 24 into it. So I guess we're looking for what's 1 over 24 first, right? So 24 divided into 1 gives us 0, 0, 4, 96, 4, so it becomes 1, 24, 16, so this can be 6, 120, 144, 16, and so on, right? So, and then there are a bunch of 6s. So, and then we still have another 4. So, again, I'm just demonstrating the spirit of not using calculator here, because if we had a calculator, then we can just, find cosine of 0.1. So this becomes 0.04166, but we're going to move the decimal 4 over, so we're going to have 5 zeros here, 1, 2, 3, 4, 5, 4, 1, 6, and we can round it to 7 here. So the final answer, our final estimate is 0.995. So that takes care of this 3, and then we have 0.04167. So we estimated cosine of 0.1. Now, we haven't used the theorem yet. How can we use the theorem when it comes to like estimates such as the one we just did? Well, let's try to use the theorem. So the theorem says that the following inequality will be true for all n, and if we choose n to be 4, that means we can use that inequality, so that is the absolute value of R4x will be bounded by m divided by, and here we have n plus 1 factorial, x minus c to the power n plus 1. So here we're going to do n plus 1 factorial, it's 4 plus 1 factorial. And here we're going to put x minus c, so c is equal to 0. So we're going to put x here. But since we're evaluating the function around 0.1, our x, the largest x gets is 0.1. So here we put 0.1 to the power n plus 1, which is 5. So m here, and I guess we'll continue we'll continue working with this inequality, but what is m? M is the upper bound of the fifth derivative of this function. So if we take this function, which is cosine, and we take its fifth derivative, so cosine of x, derivative is negative sine of x, then it becomes negative cosine of x, and then it becomes sine of x again, then it's cosine of x. But again, it doesn't matter which derivative we're looking at, that derivative will never be greater than 1, so we can easily replace that m with just value 1, because any derivative of sine cosine on any interval will always be bounded by 1. So if we choose m to be 1, then we get the following upper bound for the remainder. It's going to be 1 over 5 factorial times 0.1 to the power of 5. So we end up with something like this. 5 factorial is, again, in the spirit of not using calculator, but I'm about to give up here. 5 times 4 times 3 times 2, 4 times 3 times 2 is what, 12? No, it's 12, 24, it's 120, right? So here we have 1 over 120, and we have 10 to the power of 5, so it's 1, 2, 3, 4, 5. So basically we have 1/12, so we need to divide 12 into 1 and then move the decimal, and 12 into 1 is so 0, 12 into 10 is still 0, 12 into 100 goes 8 times, 8 times 12 is 96, so we have 40, 12 into goes, so it's 0.83, 3 times 12, 36, 40, right? So, and then we have this infinite 3's. So 1/12 is 0.0833. But we still have this, that was just 1/12. We still have to account for this 6 zeros. So here's how we're going to do that. We're just going to move this over. I'm going to put 1, 2, 3, 4, 5, 6. And you can double check this computation with a calculator. So what did we just do? We just learned that everything that has been cut off. So remember, the function is made of two pieces. So the function at 0.1 is made of the value of the polynomial at 0.1 plus the value of the remainder at 0.1. But the value of the remainder is bounded, so all that we have here is bounded by this number right here according to the remainder theorem. So everything that we have left here is less than this number. So that means that this number that we have computed earlier is within or cannot be more than this away from the true answer. So that means we got the first 7 digits, well, definitely the first 6 digits right in our computation. So us knowing this boundary for the remainder guarantees that in our computation these digits are correct. And we may be off on the 8th digit, but the first 6 or 7 digits are definitely right. And you can easily check that, so you can grab a calculator and actually compute cosine of 0.1. Make sure you put radians mode. If you use a calculator, you'll see that cosine of 0.1, the exact value is actually 0.995004165. So again, we were able to get the first 1, 2, 3, 8 digits correctly without a calculator. We just did it by hand using the fourth Maclaurin polynomial. And what did the remainder theorem allow us to do? It allows us to quantify the error that is, now we know how precise our estimate is. Now, just like we used this to bound the error, we can reverse the process here and answer this question, which is a more interesting question. So what if we wanted to be very accurate? So how large n should be? So the error, that is the difference between the actual value and the output of the Maclaurin polynomial, is no more than, and let's go for the real accuracy here, we want to get the first 20 digits right. So how big the polynomial we should pick in order for us to achieve this accuracy? And answering that question means nothing but solving this inequality for n. We already identified the value of m. So m is the upper bound for the derivative, and since we're dealing with cosine function, all derivatives cannot be greater than 1. So in our case, m is 1. N is what we're looking for. C in our problem is equal to 0 because we're looking at Maclaurin series, but C could be any value around which you center your series. And x in this case is the value at which we estimate the function. So x in our case is equal to 0.1. So if we want to estimate the value of cosine of 0.1 with this accuracy, we have to pick n such that this inequality, sorry, not this inequality, but if we make the right side of this inequality less than 10 to the negative 20, then the left side of this inequality has no choice but to be less than 10 to the power negative 20, and therefore the error of our estimate will be within the desired bound. So to solve this inequality, we just plug everything in. So instead of m, we put 1. We don't know what n is. We're looking for n, so we're going to leave n alone. Instead of c, we put 0. Instead of x, we put 0.1. And we're still going to have n plus 1 here. And this is the inequality that we have to solve. Now, to solve this inequality, we cannot do it by hand because we just don't have enough tools to solve this inequality by hand. So what we usually do is we solve this inequality with some sort of technology. And one of the easiest way is to just use Desmos. So let's open Desmos calculator, and let me show you how you can use Desmos to solve this inequality. So we're just going to create this table of input outputs. So our input is n and our output is this expression. So I'm just going to type 0.1 to the power n plus n. Doesn't like it. And n plus 1, and all this divided by n plus 1 factorial. So when n is 0, this is what we get. When n is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you see that when n is equal to 11, let me show you this whole table, right? When n is equal to 11, this expression is now less than 10 to the power negative 20. So the smallest value n can be is 11. So the Maclaurin polynomial M11 of x will be less than So again, we're looking for the output at 0.1. So this inequality guarantees that the remainder will be less than this number. But if the remainder is less than that number, that means this, as an estimate, is within 10 to the negative 20 of the true value of this function. In our case, the function is actually cosine. It's not an arbitrary function, it's cosine. So the answer to the question how large n should be so the error is no more than 10 to the power negative 20, the answer is n should be 11. So with this technique under our belt, we can now, I'm not going to do this, but it's a standard problem that can be found in any book. We can estimate the value of e, for example, right? And how do we estimate the value of this constant? Well, e as a constant is the output of exponential function at 1. So we take exponential function and we evaluate it at 1. And for example, e can be estimated by m5 at 1. So what is m5 at 1? It's just Maclaurin polynomial evaluated at 1. So this is what the actual polynomial looks like. But when you evaluate it at 1, all these x's become 1s. So evaluating e is just a matter of computing this expression. And if we apply the technique that we used for computing cosine of 0.1, here we can set any desired level of accuracy, figure out how many and how big n should be in order to achieve that accuracy, and then computing e with that level of accuracy would be just a matter of computing this numerical expression. So similarly, we can now estimate pi. Of course, we all know what pi is or what e is, but this offers us an alternative way to actually find pi rather than just taking the circumference and dividing it by the diameter. So pi can be estimated as 4 times arctan x evaluated at 1. So arctan of 1 is pi over 4. Pi over 4 times 4 is pi. And in this case, we can estimate it with, for example, 4 times m7. But again, this number, based on this exercise, can be peaked in such a way that it guarantees certain accuracy by the Remainder's theorem, which is the topic of this lesson. So once you identify your level of desired accuracy, you can identify this n, and once you have this n, finding pi is just a matter of computing this expression or similar expression, right? So if your n is 21, you would have more terms over here. But once you identify that n, it's just a matter of computing this or similar type of expressions. And this is how we can use a series to estimate accurately the values of these constants. So this would be impossible without the remainder theorem.